Good evening, everyone. My name is Megan Neer, and I'm pleased to welcome you to the Community Science and Technology virtual seminar series sponsored by Pacific Northwest National Laboratory. This seminar series is intended to introduce you to the world-class research that has been taking place right here in your community. More information and registration for upcoming webinars, as well as our new live virtual community tours, which I'll say more about at the end of the webinar, can be found on the PNNL events page, and you should see a link in the chat window, pnnl.gov/events. I'd like to pause for just a moment and do a couple of quick polls. If you turn your attention to the screen, we want to know where you're joining us from. We have a couple of areas identified. If you're from other, place it in the chat window as well. Let us know where you're calling in from. San Diego, Iowa, Portland, Oregon. San Diego again, Spokane, great. Bay Area. All right, wonderful. Thank you. And thank you, Southern Illinois and Montana. Next, we want to know if my computer will stop freezing. Maybe Cassie, you can launch the second poll for me. We want to know, are you a student? Are you in your working career? Are you retired? Just give us a sense of where you are there. Looks like we have a lot of working stage with us tonight. A few students and retired as well. All of you, thank you for joining us. So thank you for that feedback. You're going to see a survey link in the chat window at the end of tonight's talk. It would be greatly appreciated if you could take our brief survey. It helps us to make improvements to the seminar. It helps us to hear from you where you see value in these seminars, and we'll definitely make improvements based on that feedback. So thank you. And if you haven't already, this is an opportunity to sign up for emails about upcoming seminars and other community events like those live virtual community tours that I'm going to be talking about later. And also, if you're interested in viewing recordings of previous presentations, please go to the link in the chat window. We'll have chat window going on all night as far as links to where you can go for things like that. So before you learn more about tonight's topic, your presenter is going to give a brief overview of the National Laboratory System and PNNL's missions. You'll also learn more about Battelle, the operator of PNNL and the Tri-Cities' largest employer, and its staff and how they take pride in being excellent community stewards through philanthropy and volunteering. Now let me introduce tonight's presentation and speaker so we can get started. Tonight's presentation is Getting to Global Net Zero, CO2 Removal, Use, and Sequestration. Your presenter is Casey Davidson. Casey is a senior scientist focused on evaluating and deploying net negative emissions technologies facilitated by geologic CO2 storage and mineralization. Prior to joining PNNL, she enjoyed various character-building experiences, including cross-disciplinary graduate research in petroleum engineering and economics at the University of Alaska Fairbanks, and an appointment as a Department of Energy Fellow, and amateur tick inspector at the Rocky Mountain Oilfield Testing Center in Casper, Wyoming. Welcome, Casey.
Thank you so much, Megan. All right. Thank you all for joining us tonight. We'll leave plenty of time, I hope, at the end for you to put questions in the chat, but feel free to add those as we go through if there's something you hear about that you'd like to talk about more at the end of the talk. All right, so as Megan mentioned, I'm going to give you a little bit of an overview of PNNL. The Pacific Northwest National Laboratory is one of 17 national laboratories stewarded by the Department of Energy to tackle critical energy mission challenges. PNNL is one of the Office of Science laboratories, which is code speak for that's the fundamental side of the house. So fundamental science rather than application, but we do a lot of applied work, and I'll talk about that in a moment, that allows us to leverage some of that fundamental science. We get to play in both spaces. So PNNL is focused on scientific discovery in that fundamental science space and applied missions in sustainable energy and national security. And to that, we bring scientific expertise across the board. I think it's one of the coolest things about working here is that I get to work with people who are scientific experts and expert engineers from chemistry, earth science, data science, biology, energy storage, materials science, and of course on the Homeland Security side as well. So there's a lot of really outstanding expertise here, and the secret sauce is being able to put people with different expertise, different backgrounds together to solve problems that one discipline or another couldn't solve on their own. So PNNL is a very large organization. We sort of hide north of the main part of Richland, but employ 5,000 staff. We do $1.1 billion annually in business. All of that work is work that we propose for to different sponsors. We contribute as scientists to the peer-reviewed literature, so the publication number is near and dear to our heart. And we also do a lot of invention here. The patents and invention disclosures that originate at PNNL, we work to steward into the commercial space so that those can become technologies that are out making life better. We're also very, very much committed to STEM education. PNNL has a strong philanthropy and community giving commitment, and we love as a science organization in Tri-Cities and in the other communities that host PNNL laboratories, including SQUIM, Portland, and Seattle. We love to be able to give back to the people who are here as scientists who get to do this work for a living. Most of us started like these kids, getting excited about it in a science classroom or because of an extracurricular activity like Science Olympiad. So to be able to give back and kind of pass the torch and get other little kids excited about it helps us maintain that little kid inside that keeps us innovative. So to get into the heart of this talk, this is really about getting us to net zero. So you're hearing a lot of conversation right now, a lot of policy discussion. It's in the news, has been there for quite some time. This idea of getting to net zero. What does that mean? The idea is that in order for us to address climate change, we have to stop putting CO2 into the atmosphere. At that point, what we do about the CO2 that's already out there is another question, but that goal of net zero is really about stopping the behavior that has already gotten us to the point where we are. And in the Pacific Northwest, you know, occasionally I'll run across an article that says the Pacific Northwest is not gonna, it's gonna be the haven for climate change. I think those of us who live here are seeing something different right now. The record-setting, unprecedented, kind of jaw-dropping temperatures that we saw in June, here at my house, it was 116 degrees, and we had never seen anything like that before. There were villages in Canada that set records for Canada for all of time, 3 days in a row, and that village then suffered a wildfire. So this is something that we're very keenly aware of currently, and are, the implications of some of these severe weather events are being examined by other scientists, and a paper was released last week talking about the frequency of events like this in a climate change world versus a world that did not have increased CO2 concentrations, did not have increased global temperatures. And the scientists who contributed to that report also noted that while this heat dome that we just experienced in the Pacific Northwest was a once in 1,000-year kind of event, these sorts of events, if temperature continues to rise to this 2 degrees C level, we could be seeing events like this every 5 to 10 years. So for me, that brings it home as something other than something that I read about in journal articles. This is a live well, it's not live today, but it was the live wildfire map from ESRI in September of last year, showing wildfires across the West. This was sort of the apex of that wildfire season. And wildfires are an interesting thing because in addition to heat and drought contributing to the conditions that you end up with precipitating wildfire, you're also kicking emissions into the atmosphere. So there's a feedback effect there as well. So this is something that is a seasonal occurrence for us here in the West, and something that exacerbates and is exacerbated by climate change. So just to give you a sense, this is from the Clean Energy Transition Institute. These are some strategy framing documents from the state of Washington, looking at the CO2 source makeup in Washington state. So on the top left panel shows Washington's CO2 emissions by source type, and the two biggest source types there are pulp and paper and refineries. So this is non-power sector emissions, but if you look at economy-wide emissions on the rightmost top panel, both economy-wide emissions and electricity emissions need to come down, and to meet the levels that this study was looking at, need to come down to zero by 2050. That is what net zero means. That means taking our emissions from the levels that you're seeing in the solid lines there down the trajectory, or a similar trajectory to those dashed lines, to get to zero. And here to do it by 2050. And those electricity emissions are relatively low compared to the other economy-wide emissions, which is why I'm showing you pulp and paper and refineries here to begin with. In the Pacific Northwest, we have the benefit of the hydroelectric system and a significant amount of renewable generation from wind. That is projected to continue to grow. So the other big chunk of this that doesn't show in the sector or electricity piece is transportation. And electrification of the transportation fleet is critical to many of the net zero strategies that we're talking about. If you can get your electricity generation to a zero carbon footprint, and then you can electrify your vehicle fleet, you're displacing all of those gasoline and diesel emissions that would have come from running that fleet on internal combustion engines. So the burden here on the electricity system to electrify stuff that we're currently doing in other sectors where we can is significant. And in this Washington state analysis, the electricity that we generate, in addition to generating more, we're going to need to reduce the carbon intensity. So there are a lot of levers to pull, but just to kind of point out that this is a really complicated solution set. And also, if you look at the 2050 numbers that CETI projected, they're looking at a significant amount of CO2 being sequestered or utilized, 4 million tons of CO2 annually between those two categories. That's significant compared with zero that we're doing here in the Northwest currently. So this is where we would be at 2050 every year. And as the slide mentions, what all of this comes back to, in order to continue deploying renewables, in order to continue building new wind and having that zero carbon or low carbon electricity resource, and maintain a stable grid, we also need natural gas. So there is, it's not hidden. I think that those of us who work in the energy space know that the way that we currently balance in intermittent renewables is by using gas-fired generation. But it remains one of those things that I think is not as well understood in the public. So I wanted to make sure to make that point here. Natural gas, whether you're using it for peaking or for baseload power, does generate CO2 emissions. And that going forward will continue to be a key emission stream for the Pacific Northwest to address. So the technologies that I'm going to talk about today also include technologies that can be used for natural gas generation as well as some of these other sectors. So we're going to talk about CO2 capture and geologic storage, which sounds very complicated. It's got three main chunks. There's the capture part. You can capture CO2 from a lot of stuff. You can capture from power plants, as we just discussed, from hydrogen generation facilities, from fertilizer plants, chemicals, iron and steel, refineries, pulp and paper mills. If you have a concentrated stream of CO2, you can capture it. We'll talk a little bit about the technologies that go into that and some of the work that we're doing here at PNNL. Then you need to move it to wherever you're going to do something with it at. And primarily onshore, when you're moving CO2 around, you're using pipelines to do that. So again, relatively simple on that part of the story. And then what you do with it, its ultimate fate is also the storage part of that. And we also add utilization or use of CO2. There's a lot of work being done right now to figure out ways to convert that CO2 into something of value, either a fuel, the closed carbon loop idea, or to convert it into a long-lived product that will not result in the CO2 being released to the atmosphere. But what we can't use in those ways, and the market for those use cases is really, really small compared to the amount of CO2 that we would need to capture for a climate change mitigation strategy. Everything else needs to be stored long-term in geologic reservoirs. So that's typically in the mid-continent. I'll show you some maps in a minute. In the mid-continent, that happens in sandstones primarily and limestones. And the science really began in those reservoir types because that's where you tend to get oil and gas. Those are really well understood geologic reservoirs and well understood basins where oil and gas exists. And the oil and gas industry has been injecting CO2 into oil reservoirs for a long time, decades, because it turns out if you put CO2 in, you can get more oil out of the ground. So much of the science about that we use to understand how CO2 behaves in the subsurface comes out of that pedigree from the oil and gas industry. And then in the Pacific Northwest, we have a reservoir type called basalt. I'll get into more detail about that shortly. But it is distinct from sandstones and limestones and does not contain oil and gas as an economic driver to explore some of these reservoirs. So CO2 capture from industrial point sources is essential for net zero. Unless you shut off all of the point sources, being able to continue to operate without emitting that CO2 into the atmosphere is really a critical technology. This has been echoed in study after study by the National Academies of Engineering and Science, the Intergovernmental Panel on Climate Change, the International Energy Agency. Over and over again, this is reiterated in the modeling that's done, that getting to a 2-degree centigrade stabilization scenario where climate annual mean temperature doesn't increase more than 2 degrees C requires doing this CO2 capture and storage or disposal. So for a long time, CO2 capture has been kind of the sticking point because it was very, very expensive. And probably 10 years ago, the Department of Energy set a target that we wanted to get the cost of capture down from where it was around $80 a ton to somewhere in the $30 a ton range. And this paper that's shown here, this is an article that was published in Science Magazine about the journal article that PNNL researchers published. But this latest publication, which happened a couple of months ago, demonstrates the cheapest CO2 capture solvent ever shown and ever published in the peer-reviewed literature. So this is very exciting, and we're showing high-end costs on this one of about $47 a ton in a different modeling system, which we've got another paper coming out on that relatively soon. It is even lower than that. So we're really taking a big bite out of that $30 a ton CO2 capture goal and deploying this. This is developed for power plants, but other concentrated stream CO2 sources are candidates as well. Another thing that we're continuing to see in the Intergovernmental Panel on Climate Change and other groups is that some degree of CO2 removal will be necessary. CO2 removal can take many forms. There's a lot of talk right now about direct air capture, which is the first technology noted in this graphic on the left-hand side. Essentially there, you're just taking huge fans and you're sucking as much air through as possible, either over a sorbent bed or across a solvent, to capture as much CO2 out of the air as you possibly can. And there the amount of air that you can get in contact with your capture medium is the thing that defines your economics. It's very energy intensive. There are a number of projects that are investigating this right now. There are a number of technologies that are out there, but they're all very, very expensive. And we'll talk about that in a minute. Other carbon dioxide removal options include bioenergy. So if you grow biomass, it's pulling CO2 out of the air. And then if you do something with it to convert it into biofuels or to convert it into power, whatever energy carrier you want to create with it, if you can capture the CO2 off of that process, then you're net negative. Then the biomass that sucked the CO2 out of the air, you're capturing the CO2 once you combust it or whatever process you're running on it. And that is a net negative emission if you can get that CO2 in the ground or utilized into something else. So that's another one of these pathways. Afforestation, reforestation, planting trees is very widely recognized as one of these climate mitigation technologies. Increasing the amount of soil that uptake in the carbon uptake in soils is another area of investigation that's very active right now. And then understanding what happens in coastal ecosystems. Can we replicate mineralization systems at the surface that look like systems that happen in the ground to get that CO2 locked into a solid form? So quite a bit of work that's going on, but the direct air capture and the BECCS, which is this bioenergy with CCS technology, both require that the CO2 that's captured is put into the ground for long-term storage. So here's a guy named Thomas Sherwood. He was an engineer in the first half of the last century. And Sherwood noticed that low concentration stuff seems to cost more to separate than high concentration stuff. And that was so important that in 1959, he published this, which we call the Sherwood plot after Thomas Sherwood. It is still used. It still holds true. that the higher the concentration of the stuff that you're trying to get, the cheaper it is to get it. And the lower the concentration, the more expensive it is to get it. And we actually see this in the CO2 space as well, which is why direct air capture, I think, is capturing the imagination of investors, of researchers, policy folks. But we still have the reality of the Sherwood plot to have to deal with. And we see this in CO2 capture as well. So on the at the bottom of the graph here, see different technologies. These are different processes that emit CO2 at different concentrations. So as you go from the left side of the graph to the right side of the graph, those blue bars indicate the concentration of CO2 in the flue streams of each of these processes. So when you're talking about ethanol or ammonia, natural gas processing, hydrogen, those are all very, very close to 100% CO2. And so the cost of capturing them is very, very low. These are essentially compression costs at this point, because separating that CO2 out is trivial. It's mostly CO2. When you get down to the other end, natural gas fired power, you have a much lower purity of CO2 in your flue stream, and you have a higher capture cost in this graphic. And this is all based on data that I've cited in the source below. Your capture costs are north of $75 a ton for those very low concentration industrial streams. But when you add in atmospheric concentrations, which are so the concentration is so small that in order to even show it on this curve, I would have had to plot it on a log scale like Sherwood did. So the concentration of CO2 in atmospheric air is, not even visible in the blue bars, and the cost of capturing CO2 out of that atmospheric air is off the scale of this chart. $150 a ton plus, depending on which technology you're talking about and which publication you're looking at. And so Sherwood, he nailed it. The same principles that held true for all of the other things that Sherwood was looking at from an economic perspective and a separations perspective still holds true. We're still bound by that in the CO2 capture space. So direct air capture will remain more expensive than capture of CO2 from industrial sources. So getting that CO2 from point sources is a bargain compared to waiting for it to get into the atmosphere and then capturing it at that much lower concentration down the road. So I'm not going to spend a whole lot of time on this one. I'm happy to come back to it if there are questions, and it'll be in the webinar if you want to go back and look at it. But the take home here is that the top graph and the bottom graph are the same policy scenario. This is something that we modeled a number of years ago. This was the Paris Agreement with a 2° C limitation ambition. The top panel shows a world without CCS, and the bottom panel shows a world with CCS. And the way that you meet those emissions limitation targets is vastly constrained when you don't have CCS. You have to electrify everything. You have to do whatever you can to try to sequester, but your economic emissions, the emissions from your economy, have to drop very, very close to zero. And then you have to, the models do some funny things to even converge on this kind of a solution. When you have CCS, you have the option of continuing to generate electricity from a variety of fuel sources, continue to have that natural gas for peaking, to make sure that your grid remains stable with all of those intermittent renewables on it, and you have the opportunity to electrify heavily in a number of different areas. The take home from all of that, though, and if you want, I can send you the paper and you could just go to town and look at all of the detail. I love looking at the numbers. For those of you who do not delight in looking at all of the numbers, here's the take home: that without just that one technology, without CCS, you still need nuclear, you still need energy storage, you still need renewables, you still need to be more efficient with the energy that you do use. Without CCS, it costs twice as much to address climate targets. To get to the same target, all else equal, with the technology or without it, costs twice as much. And this is a study that we did, but it's been replicated by IPCC and modelers around the world. So this is a pretty robust finding. So here in the Pacific Northwest and then elsewhere in the country, in addition to, we need to get this done, there are actually some market pull technology drivers. In addition to those of us, I've been working at PNNL for 20 years. Almost all of my research has been in this space, trying to understand how this technology could play a role, where it could play a role, how to permit it, and get it deployed. So this is near and dear to my heart. Now we actually have some mechanisms that are causing people to pick up the phone and call us and say, how can I do this? I'd like to build a facility in this town in Washington or Oregon, and I need CO2 storage. Where should I drill my well? So it's encouraging that we have that kind of enthusiasm and interest, and that there is that kind of business case that's coming together regionally to drive folks to make those phone calls. So that comes down to a number of things. We have a federal tax credit called 45Q, which essentially, if you can capture your CO2 and put it in the ground or utilize it, turn it into something else, you can claim a tax credit of between $35 and $50 per ton of CO2. This is, it looks like a small number on the page, and I don't want anybody to underestimate the amount of enthusiasm that this has created. I had somebody who was very eager to do a CCS project here in the Pacific Northwest, and there are still some unknowns, which I'll get to in a minute. And he said, "Look, I'm walking away from $500 million of 45Q credits if I can't store my CO2 in the Pacific Northwest." So come on, scientists, get on it. Let's do this thing. And that was just for one project. So we're talking about really hundreds of millions or billions of dollars in some of these cases. Then we also have state energy standards. This varies state by state, but we have low carbon fuel standards. There are targets for renewable gas, for renewable power, for overall emissions from various sectors. So this is something that states are getting very active in a policy way. There's also climate aware investment. I've had conversations with firms that run funds that are exclusively for clean tech, and they're looking to fund projects that their investors recognize are a little bit higher risk, but that could be big payoff down the road because of some of these market incentives. And then, of course, shareholders are pushing their boards to internalize the climate risks that come with some of the business models that are out there. So diversifying the energy mix, for energy companies, diversifying the products that they're developing, and being really mindful of and trying to reduce carbon footprints across these processes. And then some regional challenges. You'll notice that this map, which comes to us courtesy of the Great Plains Institute, leaves out any state with a coastline except Texas and a little bit in the Gulf. The reality is that a lot of the work that's been done to date, it's been federally funded, and it's also been that long history of oil and gas industry development has really been focused on the middle of the country. There has been a little bit of work here in the Pacific Northwest that I'll talk about in a moment. But this economy-wide business case for carbon capture, storage, and transport that Great Plains is putting out there does not include our region or the East Coast or California. So there are some unique challenges that need to be addressed there, and understanding the geology and also understanding the different business cases that are not so much driven by enhanced oil recovery as they are in the mid-continent. So here's some work that came out of the now defunct West Carb Regional Carbon Sequestration Partnership. This is mapping of saline basins in the West Carb region. These look like these nice kind of homogeneous blobs, and that those should be kind of continuous. The geology in the Pacific Northwest and California is very complex. And whereas a blob like that in Illinois would speak to one thing, here in the Pacific Northwest, it speaks to something else entirely. So permitting CO2 storage, these tend to be very compartmentalized sedimentary reservoirs. And so it's not perfectly analogous. So trying to get a Class 6 permit in the West Coast states is a different animal than trying to get one in Illinois. We also have, not shown on this West Carb map, Pacific Northwest is home to a reservoir type called flood basalt. So the Columbia River basalts that are shown in this gray shading on the map on the right. If I take my dog for a walk, these are everywhere here in Tri-Cities and in Eastern Washington and Oregon. You can't throw a rock without hitting one, and the rock you're throwing is probably basalt. It turns out basalts are also uniquely suited to mineralize CO2 that's injected into them. So while we don't have the sandstone reservoirs that you have in other parts of the country, we do have this kind of value-added reservoir option that I'll talk about in a bit more detail here. So here is a wonderful photograph of Palouse Falls. Anybody who's ever been out there knows how long that drop is. That this is the bluff, from the bluff top to the river is a very long way. People go out there hiking all the time right on the edge of the cliff, and it terrifies me just to watch. So it is a significant drop. But also on the sides of the canyon there, you can see basalts exposed in outcrops. So I'm going to use that as a way to kind of explain how this works. The white shading here, these white bars correspond on the face of that cliff, correspond to different parts of the basalt flows. So here, the white bars are low permeability flow interiors. Those serve as essentially your cap rock. They don't have a lot of porosity. They cooled very, very slowly. So they have this nice dense crystal structure. And then in between those, you have these yellow zones. I've marked yellow. Those are high permeability interflow zones. And they have this collection of stuff, the fluffy, bubbly top of the flow underneath, the stuff in between, whatever sediments were laid down, and then the brecciated bottom of the flow that came in on top. So imagine putting a cold ice cube in a warm glass of water. That crack that you get, that thermal shock, is what cracked the bottom of the basalts to create that brecciated layer at the bottom. So when you take the vesicular flow top and then the stuff in between the flows, and then that brecciated stuff at the bottom of the next flow, that is your interflow zone. Has high permeability and porosity needed for CO2 storage. So that's kind of the overarching how this works. Taking CO2 and putting it in the ground, you want to be able to keep it in a supercritical state. Supercritical CO2 is very, very dense. It flows very easily, and it is kind of the optimal state for CO2 storage. This is present under the surface. You can get these conditions below about 800 meters. So for scale here, that drop from the very top of the bluff at Palouse Falls to the river level is about 115 meters. 800 meters, a depth suitable for CO2 storage, is 7 times that. So again, kind of translating that scale over onto the left side of the slide, the basalts at their maximum thickness in the middle of the basin extend to about 4,500 meters. So there's quite a lot of basalt in the inland Northwest and also a little bit kind of flowing through the gorge toward Portland that is potentially suitable for this. And actually, many years ago, one of our lab guys was interested in this, knew that there were chemistries in the basalts that could be reactive with CO2, and this was kind of at the beginning of CO2 storage as an area of inquiry for climate change purposes. And so he went into the lab and took some basalt and reacted it with CO2 and saw incredibly fast reaction rates, and said, hey, we should do this. And it's kind of a rule of thumb in science that whatever you see in the lab is going to be at idealized conditions, and it's pretty much the upper end of what you're going to see in the real world. And so the idea then was to take those promising laboratory results and see if they actually worked in the field. Can we replicate this? And so that is what we did. We injected at the Boise Cascade white paper plant in Wallula, Washington, about 30 minutes south of the lab here, and put 1,000 tons of CO2 in the ground, shut it in for 2 years, and came back to see what had happened. And it turns out that the CO2 reaction rate that we saw in the lab was pretty close to what we saw in the field. In fact, the field rates appear to be a little bit faster. So compared with a sandstone where you're taking CO2 and you're putting it in the ground and relying on the cap rock to keep it in place for a very long time to keep it out of the atmosphere, here you're putting it in, and some recent modeling that we've published suggests that about 60%, more than 60% of the CO2 that we injected was converted into a mineral form within 2 years, and that the vast majority of it would be converted to minerals within a decade, compared with some of these other formation types where that CO2 remains supercritical for decades, centuries, millennia. This is very, very, very interesting, and of a lot of interest for developers who are looking to find CO2 storage opportunities that minimize their risk, and in particular their long-term financial risk associated with having to monitor one of these sites for a long time. So this is essentially says what I just said. The other piece of this is that the regulations that are used to inject CO2 into the ground and keep drinking water and other resources safe are under the Safe Drinking Water Act. The type of permit is called Class 6, and Class 6 is really written for sandstones. So there's work that still needs to be done to help understand how to permit a Class 6 well for CO2 storage. So just some of the old questions when I started in this job 20 years ago were things like, is there enough CO2 storage capacity? And work that was done here and elsewhere shows that yes, in most places, there's enough storage capacity. Does it match the potential demand? And the answer there is yes. In most places, you have 100+ years of capacity to meet demand from existing sources and potentially future sources as well. How much could it cost? At the time, there were orders of magnitude of errors, uncertainty on those cost estimates, and we showed that most geologic storage is available for under $25 a ton, and where that capture cost can be minimized, then you're getting into the range where Class 6 or a 45Q project might actually yield profit from that 45Q portion. Can R&D reduce capture costs? Because those looked very daunting. And we've shown, as I mentioned, we're now below $50 a ton for sure, and probably below 40 when we model it in the new system. How do we permit and verify? That Class 6 permitting application type didn't exist 20 years ago. That was the result of a lot of science that's been done since then here and elsewhere. And we're very, very proud that now when industry calls us and says, hey, we want to do one of these things, we already have a common language where we can talk about the Class 6 permitting process, and they're kind of already smart about that. And will it work in diverse settings? The answer is yes. We've got CO2 storage deploying around the world right now. I would love to talk about all of these things. I really do just want to hit on a couple of them. Developing the Class 6 basalt storage to help meet our regional targets. This is something that PNNL has taken on as one of our transformational outcomes that's associated with our CO2 RUS, which is CO2 removal, use, and sequestration focus area. We really want to get this done. We started it at Wallula. We want to carry it across the line to the point where it's permittable under Class 6 and well understood in the region. We want to quantify and validate carbon storage in ecosystem restoration. This is something that is a uniquely coastal issue, and we have some amazing capabilities at our Coastal Sciences Laboratory in SWIM. So we're very much focused on that. And then developing the tools for the workforces that are going to support these things. We're doing some work right now to integrate artificial intelligence, machine learning into real-time operations technologies so that you don't need a PhD and 20 years worth of experience to run one of these projects or to write a Class 6 permit application. So very excited about all of these things. And then bringing it full circle, this is already outdated. I grabbed this screenshot from ESRI yesterday. This is a wildfire map, and there are now 2 more in Washington State that are not shown on this map. Wildfire season is in full swing here. It continues to be a challenge. Most of the time when we're talking about climate change mitigation, we're talking about doing such and such by 2050. But this is something that we're facing right now, and that becomes an adaptation question. So it also creates opportunities for innovative business models. I have permission from the Yale Carbon Containment Lab to share this idea that they have. This is a conceptual, notional idea for a business case called Project Traprock that uses an integration of technologies to address problems that we have right now. Forestry management, what do we do with the surplus fuel that is driving these wildfires, because the forests have excess stuff in them that we could go get, but what do you do with it once you get it? The idea here is to take that forest biomass, clean up the forests, reduce the fuel that is in the understory to feed these wildfires, and do something with it. Take that as biomass to convert it into biofuels or to biogas or whatever that finished product is. And then at the same time, take the CO2 that's generated in that process, put it in the ground for net negative emissions that then you can bring in various revenue streams from the forestry management piece, from the biofuels themselves, from low carbon fuel standards, from carbon offset trading markets, from the 45Q tax credit. So we're seeing these really inventive approaches to not just doing, plunking down a CO2 source and a CO2 storage project right next to it, but thinking about how we can meet a lot of different needs with a variety of technologies to address some of these very unique Pacific Northwest and Western United States challenges. So they wanted me to be very clear. This is notional. They're just, they're still thinking through this and trying to understand how it might work. But I thought it was a cool example of some of the imaginative approaches that people are taking that hopefully will be enabled by some of the technologies that we're working on here at PNNL. And then moving beyond net zero, I would like to see in my lifetime, this is, again, conceptual, I would like to see the Pacific Northwest not just be the first to get to net zero, but also to be the first to move beyond net zero and start working on net negative emissions. We know that will be something that will be necessary, hopefully not as necessary as it might be if it takes longer to really take action globally than the modeling would suggest. But this idea of building an innovation hub. There are so many developers who are interested in siting their project in the Pacific Northwest, but they need to have a CO2 storage reservoir to do that. And I know of a number of projects that have not come to the Northwest because they could not easily say, I can get my Class 6 permit the way that they could in Texas or in Illinois or in Ohio. So bringing clean tech to the Northwest is important, and having a facility where folks can come and site as an incubator of, here is a space that we've permitted CO2 storage. You can leverage existing data, you can leverage existing wells if there's capacity to really start to attract some of these next generation technologies to our region. So with that, I am happy to take any questions, and I cannot see the chat, so I'm going to have Melissa and Megan and Cassie hopefully read me questions.
Well, thank you, Casey. We have about 55 people on the call tonight, and we do have some questions that have come through, so I'll go ahead and get right to it. Can you please discuss potential risks of carbon capture technology and ways to mitigate them?
Carbon capture technology, I think just the CO2 capture risk is quite low. By pulling CO2 from an industrial stream or from the atmosphere directly, that's a known chemical process. Obviously, we're working on the efficiency and the cost of it, but that piece of the puzzle is safe, understood, and certainly manageable. I think there's some concern about solvents. Some of the solvents that are used are not necessarily the most environmentally friendly chemicals in the world, and that's one of the things that PNNL has been working on, is developing solvents that are less environmentally harmful. And in fact, the head of our CO2 capture program, Dave Hildebrandt, really focuses on green chemistry. How do we develop green solvents that are as low impact as possible while also doing the job that we need them to do?
Okay, thank you. And are there potential risks of the carbon storage technology too?
There are, anytime you're doing something in the subsurface, anytime you're doing any kind of energy development, there are always risks. With an understanding that was a question that folks were going to be asking, certainly a question that we were asking 20 years ago. Every field project that I've worked on, every siting discussion that I've been a part of, risk comes up, and what is the risk of subsurface storage? So Department of Energy has been funding the National Risk Assessment Partnership for close to, I think we're getting close to 2 decades on that one as well, which is really about coming up with tools that operators can use to understand and manage the risk from these projects. The big risks tend to be mobilizing brine from the reservoir that you're in and pushing it out or pushing it up. Or of course, your CO2 moving out of your storage reservoir is another one that we monitor for, we model for. So in order to get a Class 6 permit, you need to have a lot of data on your reservoir and understand how it's going to behave in response to CO2 injection. And then you need to model what you're seeing in your observational data. You need to be able to show that your modeling converges with that. So you need to have good agreement between what you're actually seeing in the reservoir and what you thought you were going to see in the reservoir to keep your permit and to make sure that you're compliant. So there are a lot of checks on that, and understanding how pressure changes and how we can mitigate those pressure increases is another big piece. So all of those technologies exist. I think to a large extent, I think just making sure that scientists are really crisp about how we communicate that with the operators and with the stakeholders in the areas around these projects is really, really important. Because it's one thing for me to say, we know how to manage that. It's something else to be able to show that we're doing that in an effective way.
Okay, thank you. If about 60% of the CO2 is mineralized in basalt within 2 years, what happens to the remaining 40%? Does it just take longer to mineralize, or is it lost or re-released?
So it just happens that 2 years was kind of an arbitrary number. That's when we went back in, re-entered the well, took samples. It was 60% at that moment in time. But extrapolating that rate out, we anticipate that we're very close to 100%, or you're never going to get 100%. There are going to be little bits of CO2 that are trapped, but they're still immobile, but not necessarily converted into a mineral. We anticipate that plume is immobilized either by mineralization or by just lack of ability to move around within a decade for that 1,000 tons that we injected.
Okay. Are any patents open for these CO2 to mineral conversions? What minerals?
These are natural processes. So I am not sure about IP. I know that there's a lot of interest in doing storing CO2 in the basalts results in what's called in situ mineralization. There's a lot of interest in ex situ mineralization. Can we replicate these processes in a cost-effective way at the surface? And you get into the question of life cycle analysis, and if you're mining a bunch of basalt so that you can grind it up into powder and then run CO2 across it to turn it into anchorite, or whatever reaction product you have, are you actually contributing to pulling CO2 out of the atmosphere or reacting that CO2, or are you reducing your overall emissions impact because of all of those other life cycle costs that come into it? But there's a lot of interest right now in figuring out how to mimic that natural process to do something that could be commercialized at the surface.
Okay, thank you. And we are almost at the top of the hour, so I will ask you one last question. What is Class 6 a class of?
That's a good question. Class 6 is a class of underground injection control program permit. So there are, prior to Class 6, which is the newest one, there were 5 classes. anytime you're going to inject anything into the subsurface, whether you're injecting water or you're injecting steam, if you're doing it for oil and gas recovery, if you've got excess water that you're trying to get rid of, all of those require a UIC permit, that underground injection control program. So class 6 is specific to injecting CO2 into the subsurface, but it is one of a family of subsurface injection permit types.
Okay, Casey, thank you. We appreciate you taking time out of your day to share your research with the community, and we thank all of you for joining us tonight for tonight's seminar. So I'd like to remind everyone one last time to take our brief survey. The link is in the chat window, and at the end of the survey, you can also sign up to receive notifications about future seminars and the live virtual community tours. And speaking of the live virtual community tours, we are hosting an 8-week series of live virtual tours that will take you through a number of labs on our Richland campus, where you will learn more about nuclear explosion monitoring, the science and hardware behind machine learning and artificial intelligence, our work in nuclear energy and environmental management, and so much more. You can learn more about the live virtual tours, including information about registering, by clicking on the link in the chat window. Again, thank you to everyone so much for joining us tonight. We really appreciate you taking time out of your busy schedule, and we hope to see you at our live virtual community tour starting July 28th. And thank you, Casey. We appreciate your time. Everyone
Thank
have
you
a
very
great
much.
evening.
Stay safe, everybody.